Okay, welcome back to the second video in a series on differentiation. In the last video, we looked into the foundational rule of differentiation, something called the power rule, and how to apply it so that we can differentiate polynomials. We established what the rule is and where it comes from. In this video, we're going to look at, in more depth, how to apply that to a wider range of functions so that we can tackle coefficients, constants, and terms that aren't immediately in the familiar power form. So we'll use the rules of indices to be able to get them into a form that enables us to do the differentiation. So just one main learning objective for this video, which is to be able to apply the power rule to differentiate polynomials and other functions. First of all, a quick recap. In the last video, we discovered that if y equals x to the power n, then what we do is we basically bring the power down to the front and reduce the power by 1, giving us dy by dx equals n x to the power n minus 1. So that's the standard rule for differentiation, which we apply to every single problem that we're going to look at here. Just a quick recap of how that works. So let's say, for example, we had y equals x to the power 5. What we would do to differentiate is bring the power down to the front, so the 5 would come down to the front, and then take 1 away from the power, so the power of 5 would become the power of 4, giving us 5x to the power 4. So it's a fairly straightforward rule to be able to apply. Now, what if we have a coefficient in front of our polynomial? So remember, a coefficient means a number that's being multiplied on the front of the polynomial. Like, for example, 3x squared, 3 would be the coefficient of x squared. So if we have y equals a x to the power n, then a would be what we're referring to as the coefficient. All that we do is bring the power down to the front and multiply it to that coefficient. And then, just as before, we take 1 away from the power. So basically it would be n times by a, that would become the new coefficient, and then x to the power of n minus 1. So let's take an example. Let's say we had y equals 4x to the power 3. What we would do is, first of all, bring the 3 down to the front, so we would end up doing 3 times 4, and then we'd take 1 away from the power, so instead of the power of 3, it would become the power of 2. So 3 times 4, x to the power of 3 minus 1, and if we simplify that down, we'll get 3 times 4, which is 12, and then 3 take away 1 is 2, so 12x squared, 12x to the power 2. What about if we have a slightly, in some ways, more straightforward one? If we had y equals 5x, this is the first instance where we need to remind ourselves of maybe some of the rules of indices. Remember, if an x doesn't have a power, we can give it a power. We can give it the power of 1. X and x to the power 1 are the same thing. So instead of 5x, I might think of that as being 5x to the power 1, and then I can apply my rule of bringing the power down to the front and taking 1 away from the power. So it's going to be 1 times 5 on the front, and then the power of 1 will instead become the power of 0. So I get 1 times 5, x to the power 1 minus 1, which is 5x to the power 0. And again, another rule of indices, anything to the power 0 is always equal to 1. So we've got 5 times by 1, which of course is just 5. Now, we've gone through that a fairly long process, but normally we would probably just be able to cut straight to saying, if we've got 5x and we differentiate it, we go to 5. We'll see that that rule applies. So if I get y equals 7x, if I differentiate it, I'm going to get 7. If I've got y equals 100x, if I differentiate it, I'm just going to get 100. So it becomes a fairly straightforward thing to differentiate when you know what you're doing. And the other rule we talked about is, what are we going to do if we differentiate a constant? So what we mean by a constant is a term that doesn't have an x in it, like y equals 2 or y equals 7 or y equals minus 3. Now, if you think of this from a graphical perspective, y equals 2 is a horizontal line at y equals 2. What's the gradient of that line? A horizontal line has always got a gradient of 0. So it makes sense that no matter what the x value is, dy by dx is going to be equal to 0. And so essentially, if you differentiate a constant, you're going to get 0 every single time. If you have y equals c for constant, then dy by dx is always going to be equal to 0, no matter what the constant was. Okay, so these are all rules that once you get familiar with this, they become quite natural. You can apply them quite quickly and easily. Now let's have a look at just some slightly more challenging ones when you have to use the rules of indices to be able to get something into power form and so that you can differentiate them. Just a quick refresher of the rules of indices that you've encountered previously. First of all, with roots, let's say we had, for example, the square root of x. The square root of x is x to the power of a half. If you have the nth root of x, then it would be x to the power 1 over n. So, for example, the cube root of x would be x to the power of 1/3. The fifth root of x would be x to the power of 1 over 5, and so on. The second rule is how we approach reciprocals. So reciprocals means when you've got a number being divided by x or divided by x squared or something like that. And the rule that we need to apply there is 1 over x to the power n is the same as x to the power negative n. When you have a negative power, it means you take the reciprocal of that term. So these are going to both be useful because if we get something as a root or reciprocal, we can write them using a power, and then we can use our rule of differentiation and easily differentiate. And sometimes we might need to use combinations. So for example, if I had 1 over the square root of x, I need to get a negative power. That's what gives me the reciprocal part. And then to get the square root part, I need the power of a half. So x to the power negative a half would be the same as 1 over the square root of x. So this tends to be when these questions can just get a little bit more challenging, is actually the application of the rules of indices that we need to be really careful with. Let's just take two final examples to finish off this lesson. So the first one, if I differentiated y equals the square root of x, my first step would be to rewrite that so it's x to the power of something. So I know that this is going to be x to the power of a half. Then I can apply the normal rule of differentiation, which is bring the power down to the front and take 1 away from the power. So the half comes down to the front, and then if you take 1 away from a half, you get minus a half. A half take away 1 is minus a half. So we've got a half x to the power of a half minus 1, which is a half x to the power minus a half. And then what we should aim to do as our final line of working is write that in a better form. We want to try and, instead of writing x to the power minus a half, we want to write that as a reciprocal or as a square root or something like that. So we know that x to the power minus a half is the same as 1 over the square root of x. And so if we put that all together, we've got a half times by 1 over the square root of x, which is 1 over 2 square root of x. And that would be our final answer. Let's look at one final example, which is when we've got a reciprocal. So if we had y equals 1 over x squared, we would start out step 1 rewriting that so that we can apply the power rule. We need to have it in the form x to the power n. So we're going to write this as x to the power minus 2. 1 over x squared is the same as x to the power minus 2. Then we can apply the rule of differentiation. Bring the power down to the front and take 1 away from the power. Minus 2 take away 1 is minus 3. So it's minus 2, x to the power minus 3. And finally, we'll rewrite that in a slightly nicer form. We know that x to the power minus 3 is the same as 1 over x cubed. So 1 over x cubed, we're timesing that by minus 2, giving us minus 2 over x cubed is the nicest way that we could write that down. So final answer, dy by dx is equal to minus 2x cubed. So I hope those examples give you a clear idea of how we can apply this power rule in a few different situations